Hi everybody, welcome back. We were talking about conservative forces and non-conservative forces, and in the previous segment we just did an example where we had a conservative force taking various different paths. All right, this is going to be a non-conservative force taking actually the same two paths. In the previous segment, the object went up and then over, and then it went this longer path right here. But that was a conservative force of gravity that we were acting against. We were moving it up and over and so forth. Here, this kind of crosshatch in the background right here indicates that we're looking down on top of, almost like looking down on the floor. It looks like a basketball court, almost, all right, with the boards on the floor. And so the force we're dealing with here is going to be kinetic friction. The friction between the floor and the object that you're sliding over the floor, all right? So this is really an over the head, or you might say a bird's eye view, looking straight down. And we're going to address that in just a minute. But real quick, let's just kind of refresh on the work done by friction. You know, I don't like that color. I'm going to go back to red again. All right, the work done by friction. Okay, well, if we have, draw this over here on the right. We have a box right here, and we're applying a force to it. So force applied. What direction does friction always act in? Well, it always acts against the direction of attempted motion. So that's your kinetic friction right there. And yet the kinetic friction is created by the fact that, well, we've got mg acting downwards, and then the normal force between the floor and the box. So Fk, the kinetic friction force, is really the coefficient of kinetic friction times the normal force, which in this case actually equals mg. All right, mu k times mg. So that is actually going to be the friction force that is acting right there. So we want to find the work done by friction. It's going to be mu k times mg, creating the downward force, which creates the supporting force, the normal force. So this is the actual friction force, and then we have to multiply that by the distance it is traveled, right? The distance that it moves. And we have to multiply it by the cosine of the angle between them, phi. All right? Now, think about this for a second. If you're pushing a box around the floor, you set it down the floor and you push it, regardless of what direction that you push it in, what direction does friction act in? It always acts against the direction of motion, right? Friction inhibits your motion. So for this little segment right here, for part one, or well, for line one, you're moving it this way as indicated by the blue line, but friction, kinetic friction, is acting against. Here, kinetic friction is acting against the direction of motion. Here, kinetic friction, here, so whatever direction indicated by the blue line the object is moving, kinetic friction is acting against that. And so that means that for any I messed that one up right there. Okay. For any segment right here, there's always going to be a 180-degree difference between the direction of motion and friction. So our phi, when dealing with friction, is pretty much always going to be 180 degrees. All right. Now what I'm going to have to do is I'm going to shrink this down a little bit because there's not a whole lot of space to write. But we're going to find the work done by friction taking path 1 and then by taking path 2. So I'll see if I can write in red and then also write in purple as well to kind of color code that. But I am going to shrink this down a little bit. So let's do that right there. I think I have enough space. All right, maybe a little smaller. All right, so we have the we have the mass of the box. And in fact, this is probably the same box as the previous problem, right? And we also have the coefficient of kinetic friction right here. Well, let's do path 1. It looks like it's red. Maybe it's orange. I don't know. I'm going to write in red. So the work done, the net work done by friction, Fk, for path 1. Like I said, that's another crazy subscript right there. But we're being specific about what work we're talking about. All right. Well, it's going to be mu k. You know what? I'm going to write my values in right here because if I just write my general terms out first, I'm going to run out of space. What is our mu k, our coefficient of kinetic friction? That's 0.63, right? Okay. times our mg. So that's 4.57 times 9.81. All right, let's write that in. 4.57 times 9.81 times the distance moved. This first segment right here is 1 meter. So 1.0 meters times a cosine of what's the angle between the friction and the direction of motion? It's always going to be 180 degrees. Okay? Cosine of 180 is -1. So that's going to make each of these negative. Friction always acts against. It always does negative work on your direction of motion. So we're going to see that play out right here. That work plus, oops, I'm trying to write with my laser again, plus this work done by friction right here. Okay, so we're moving it up, friction is acting against. Here we're moving it sideways, friction is going to be acting against here. Let's key in our values. 0.63, right? So coefficient of kinetic friction, 0.63 times 4.57. That's our mass times gravity, 9.81. Times, how far are we moving it right here? 3 meters. 3.0 meters. Oh, I don't need to write m in there. 3.0 times a cosine, once again, of 180. That gets us from A to B. What do we get if we calculate all that together? We get about 113 joules. But it's negative, right? Negative 113 joules of energy. The work done, the net work done by kinetic friction in segment 1 right there. All right, so no matter where you push it, friction acts against you and it robs your system of energy. Let's see if we get the same thing going from A to B by way of a different path. And with friction being a non-conservative force, I think we're going to find that we will not. I'm going to do this on the right-hand side. I'm going to do it kind of vertically since I don't have a nice horizontal space to write, but the net work done by kinetic friction for path 2 is what right here? Well, all right, we're going from here to here, so that's going to be our 0.63 times 4.57 is 9.81 times the distance of that first segment at the bottom, that's 6 meters, 6.0 times a cosine of 180. All right. Plus our second work here, so from here to here. You guys getting tired of writing all these things in? There is going to be an easier way to do it a little bit later on. In fact, you can factor out some of these recurring values, but we're just going to write them all in for now, and you can come up with your own simpler way to do it. Segment 2 of that purple path, 0.63 times the mass, 4.57, 7 right there, times 9.81, times, what's our distance to the second segment? That's 2.0, right? 2.0 meters times a cosine of 180. Plus segment 3, 0.63, 4.57 times 9.81 times this distance right here is 3 meters, 3.0 cosine of 180. And our fourth segment from right here to here is going to be plus 0.63 times 4.57 times 9.81 times 1 meter times cosine of 180. Okay, what's that going to add up to? Now, all these cosines and 180s is going to be -1 plus something times -1 plus something times -1. So this work that is being done by friction is going to be getting more and more negative the further you push it. So 0.63 times 4.57 times 9.81, all right, times, what you could really do is factor all those out, times -1, and then just multiply that by the various distances. 6 plus 2 plus 3, it's 11, plus 1 is 12, times 12 meters it has been moved through. And I get a grand total of negative 339 joules of energy done, or the work done by, the kinetic friction right there. So very different from the shorter path. I guess the moral of the story here is if you're going to be working against a non-conservative force, a force that robs your system of energy, you might as well do it for less amount of distance. Right? So you lose less energy going from here to here than you do from there to there. And that makes common sense. I mean, if you're going to move something across the basketball court or across the floor, this is a much smarter path to take. Otherwise, if you drag it across the floor here and then up and then over, you're kind of wasting your energy. Well, that's literally true. Friction is causing you to waste a lot more energy the longer the path you take. All right, so it's example 8.2. And it shows a difference between non-conservative forces like friction and conservative forces like gravity and springs. So, thanks for following along. And if you have any questions, make sure you come see me. But we're going to continue on the next video in the following segment. So, hope to see you then. Thanks. I'll see you later.